Hello, everybody, and welcome to this first half of lecture 9. Since basically we have gone over the time of the course, the material here will not be examined. So really, don't worry about it. It's here just for your interest, so that we're just one lecture away from the final idea of the course, basically linking root systems and the classification of semi-simple algebras. So yeah, I wanted to put this here just for your interest. It will not be examined. Okay, so we remember the last time we had looked at root systems. We've been doing this over a few lectures. Just to recall what's going on here, so let E be a finite dimensional Euclidean space, let delta be a root system. Okay, Euclidean space is just going to be a real vector space together with an inner product. Okay, or equivalently an orthonormal basis, and we let delta be a root system. Now we call R the dimension of either rank, if you remember, and we also remember that this root system was going to be it spanned the vector space, but the elements were not linearly independent. And this base was somehow a linearly independent subset that spanned not only the vector space, but also spanned the root space in a certain way, an integer kind of, and allowed us to define positive and negative roots. So every element should be a linear combination, an integer linear combination, where all the coefficients are either positive or either all positive or all negative. Okay, that was what we that's what a base was. So now what we're going to do, we showed well, what we're now going to do is to associate to the data of a root system together with the base. We're going to associate something called its Cartan matrix. So it's basically to understand these root systems. There are a number of things. So for example, we saw that associated to any root system, we had its Weyl group. So that was one way of abstracting information from the root system to produce something that looks a little more familiar, a group. The Cartan matrix is a way of abstracting from the root system a matrix that gives us another way of looking at the root system. Because I guess when you eventually go back and associate them to semi-simple algebras, the combinatorial data somehow inside in the root system, it's good to have a number of different ways to look at it. Very useful. And in particular for the classification, this is a major step. So it's the Cartan matrix for a base of a root system is going to be the R by R matrix, which has got entries A sub ij, and they're given by this, which is now familiar quality. Remember, this was in the definition of the root system when we were defining the reflections. With respect, we're taking a reflection of the root system with respect to a choice of root. And this is how we define actually the Cartan matrix. Okay, so it's defined in terms of, we take the inner product of the two roots, A of ij, two simple roots. I mean, the Cartan matrix is with respect to a choice of base. And then we divide it by this alpha of ij, okay? So you see in particular that this in general will not be symmetric, because it can happen that the alpha of ij's, the alpha ii and the inner product of alpha sub I and alpha sub I has a different value, which is to say the root vector has a different length than alpha sub j. So it's not symmetric. For example, in the A series root systems that we've been using as an example, it is symmetric, but that's not true in general. Okay, but what is true in general, what we can see from this is that alpha ii is always equal to 2. Okay, that's immediate, because you put in alpha here, the two of these cancel, and of course you get 2. The alpha ii is going to be less than 0 for all I not equal to j. It's not immediate. We'll see the proof in the following slide. But if alpha ij is equal to 0, then, and only then is alpha ji equal to 0. Because of course it's an inner product, so this is always going to be non-zero. It's going to be a strictly positive real number. But this is going to be 0 if and only, I mean, the inner product itself is symmetric. So we see that alpha sub I and alpha sub j, that inner product is going to be 0 if and only if the inner product of j I is going to be equal to 0. So this one is also clear. And from the last one here, well, that goes back to previous result where we were classifying, if you recall, the values that can actually appear in the root system. So let's see the proof. So as we said, the first one is clear. Now, it was proved in the last lecture that for any two simple roots, their inner product is always going to be less than or equal to 0. Okay, this was always true. Now, the inner product of alpha and alpha, which is below the line, that is always going to be positive because it's an inner product. We have positive definiteness in the definition of an inner product. So that means that the overall fraction that we have, that's going to be 0. Sorry, it's going to be negative, less than 0, less than or equal to 0. Okay. No, as we said, it's clear from the definition of A of ij and the fact that the inner product is symmetric because it's an inner product, that one is 0 if and only if the other is 0. And finally, for these values that we get for the Cartan matrix, we calculated the values of the inner product of alpha and beta, the angles that exist between the roots. These were calculated in the last lecture. We saw that these angles, the possibility we had for them, we got that actually the product of was going to be lives inside the set 0, 1, 2, and 3, and that immediately implies here that this is going to live inside 0, 1, 2, and 3. Okay. So just go back to the previous lecture where we classified the angles, and you see inside in the proof here that we produced this set of 0, 1, 2, 3, and that immediately implies that the product here is going to be in 0, 1, 2, and 3. Okay. So you notice the product here is interesting because then, I mean, these are just numbers. So that sort of removes the asymmetry that you have around the diagonal in the matrix. Okay. Now, the Weyl group has generators. So now here's the theorem. Now, once we've actually introduced these values here, okay, these A of ij's and A of ji's, it gives us, how would we say? It gives us the notation, I guess, in which to state this theorem, which allows us to give a concrete, explicit description of the Weyl group associated to any root system. Okay, so the Cartan matrix is central to this. And what does it look like? Well, it's going to be the free group with OR generators, subject to the relations generated by these two. So we've got s squared of I is equal to 1. And we've got s sub I, s sub j by m sub ij is equal to 1. Where, now this is m ij, it's not the A of ij in the Cartan matrix, but there's this convenient table to translate between them. So as we just saw, the A sub ij and A sub ji, these will actually have to live inside in set 1. They'll have to, the only choice that you have is 0, 1, 2, or 3. Okay. And what is m of ij? Well, if it's 0, it's 2. If it's 1, it's 3. If it's 2, it's 4. And then if it's 3, it's 6. A bit of a jump there, but that's how things work. Again, we won't prove this since this is like a bonus lecture, and we try to keep things as concise as possible. But you know, the proof is not terribly complicated. But it gives us, it shows us that once you know the Cartan matrix, you can describe the Weyl group very explicitly. So what if we go back to our example, the one that we've been using all along? So let's recall the root system A sub n, and the roots here are going to be alpha of ij. So it's E of I minus E of j, where E sub I is going to be the orthonormal basis with respect to the inner product on our Euclidean space, okay, in a real vector space. And we can take a simple roots. I'm going to choose the simple roots of alpha e sub I minus e sub I plus 1. So again, we see that these span the whole root system in the appropriate ways, integer combinations. Because you can easily, just by adding up enough of these, the integer coefficients are just going to be +1 or -1. And you can see if you add up enough of these, you can get anything of this form. Okay. These are, of course, they're multiplied by -1. So from this, what does the Cartan matrix look like? Well, the Cartan matrix is A of ij. It's the matrix with entries A of ij. We've got 2, we've got alpha sub I, alpha sub j, divided by alpha sub I, alpha sub I. Okay, but this, remember that, well, you don't need to remember, you just look here. If you take the inner product of alpha sub I with itself, well, this is going to the inner product of this, and this, of course, is going to be 0 because it's an orthonormal basis. So this will just pair with itself to give you 1. This will pair with itself to give you the 1. The 2 minuses will cancel out, and you're left with 1 plus 1. So the length of this root is actually just 2. Okay, and then the 2 and the 2 cancel. What do we get? We get alpha sub I, alpha sub j. So the Cartan matrix here is actually the same thing as just the inner product on the simple roots. Which, of course, if you see, just looking at this again, the only way that they can have a non-zero pairing is if either j is equal to I minus 1, so it looks like I minus 1, or it's I plus 1. And in both cases, you get a -1. Okay, so only one of these, of course, can be non-zero, obviously. So that means that most of the time the Cartan matrix is going to be 0. Remember, of course, the A of ij, we haven't calculated the A of ii here because, as we saw in the previous, it's always 2, so we don't need to calculate it. But it's basically just you have the diagonals are 2 and the off diagonals are going to be -1. So let's just look and see what this is by writing the example. You see, for the first one, it's just 2. Very easy. We have no off diagonal because the rank is just 1. Here, it's 2 and 2, and you have -1 off the diagonal. Here you see it's 2 along the diagonal, and then it's a -1, -1, and -1, -1, and up here you get 0. As you go up to larger orders, it's mainly zeros, but it's always like this: a 2 down the middle, and then on the sort of the diagonal above the central diagonal, you're going to get -1s. The diagonal below the central diagonal, you're going to get -1s, and everywhere else you're just going to get zeros. Okay, so mainly zeros. But now that we have this, and now that we see what the Cartan matrix looks like, we can calculate the Weyl group explicitly using the previous theorem. We observed before, we weren't 100%, we didn't give maybe an extremely careful proof, but we observed before that the Cartan matrix was the symmetric. So let's see if we can reproduce this result from the previous description, explicit description of the Weyl group. Okay. So we see that it's generated by elements 1 up to n-1. Okay. The n-1 here is the rank of the vector space. So it's actually R to the n-1. And it's subject to the relations s squared. So let's write out what they are explicitly in this case. We get s squared is equal to 1. S sub I, S sub j is equal to, it commutes with, Si and Sj commute with each other if I is greater than 1. Okay. So that's just because we've got a 0 basically in most of the entries. And then finally we have that S of I and S of I plus 1, the 3 are equal to 1. And we see that this is just the symmetric group. Okay, so actually maybe we should look, I should give you a little bit more detail about this. Okay, it's easy. So what's actually going on here is in this one. Okay, so if the Cartan matrix, if we get a 0, which of course is going to happen if we have 2 simple roots, then we know that their inner product is going to be 0 if they satisfy this condition here, okay? It's only when they're within distance 1 between each other that it's non-zero. So if they're greater than 1, that means it's 0. What does 0 correspond to? Remember in the Cartan matrix, we could transfer between, in the table we had in the theorem about the Weyl groups, the quality 0 corresponded to 2 in the relation. So what this is saying is that we're going to get a relation S of ij like this, okay, and it goes here, and 2 is equal to 1, the identity of the group, all right? But if we combine that with the fact that S squared, and of course this means that Si is equal to S inverse. So here we're just going to get Si, Sj, Si, Sj, Sj, and Si, Sj, and this is equal to 1. Okay, so now if we bring these across to the other side, and we're going to get this, using, of course, the fact that every Si is going to be equal to its own inverse. So what we get, these are just the defining relations for the symmetric group. There you go. And in fact, it turns out that for all of the root systems, well, except for a finite number, the Weyl group looks quite close to the symmetric group. It's some semi-direct product of the symmetric group. Okay. Now, so what we just did was we associated to a root system. We associated this group. Okay. That's extremely useful in studying that basically describes the symmetries of the root system. Now we're going to associate another object, a new object, to a root system, and this is called its Dynkin diagram. This is a very, very important graph, I guess, a diagram that you associate to a root system. It started off in like this in the theory of Lie algebras, but mysteriously it turns out to arise in many other areas of maths. And it's somehow this fundamental combinatorial structure that was discovered in Lie algebras, but has been shown to have connections with many, many other areas of maths in a very mysterious way. So they're amazing things, but they're very easy to define. Okay, so we just take a root system. We define them in terms of choice of base, just like the Cartan. But just like the Cartan, I didn't mention this, but just like the Cartan, the Dynkin diagram is independent of the choice of base. So if you pick a different base and then you go through this procedure and you construct the Dynkin diagram, it will actually be the same for two different bases. It won't change. Okay. It's independent of the choice of base, which is good because it should really be an invariant of the root system and it shouldn't depend upon any choice that we have to make. So what are the diagrams? So a diagram is going to consist of vertices and arrows, edges, I should say. Vertices and edges. So for each, I guess for each simple root, I could really say, because it's dependent. The number of vertices are given by the dimension of the Euclidean space in which the root system lives. But that's the same as the number of elements in your base, the number of simple roots. So you can basically we're looking at something where we've got a vertex for each simple root. And now the number of edges between two roots is going to be given by this quantity here, which is, if you recall, when we were introducing the Cartan, when we gave our first results about the Cartan matrix, this quality here was shown to live inside in the set 1, 2, 3. This is what it is explicitly. So remember, this is the Aij. We've got the 2 here. We've got a 2 coming from here and a 2 coming from here. That gives us the 4. We've got an alpha ij and an alpha ij squared. I mean, here the order is different, okay? But it's an inner product, so it's symmetric. So in fact, you can switch them and you just get the square up here. And then below the line, we've got this ij and ji here. So you see that it is this quantity is symmetric in the I and the j. But we saw, let me write this in, that in fact this quantity has to be an element coming from our classification of the angles in the previous lecture. We saw that this quality has to live inside in 0, 1, 2, and 3. Right. Yeah. So, and then finally, it's got a little bit extra. So it's not just an ordinary graph. It will have an arrow, and the arrows are actually not. It's not that. If the roots of different length, which is to say, if this quality here is different. Okay, so if this is not equal to this, then we want to be able to see this in the diagram. Okay, you want to be able to see which of the simple roots is larger. And in that case, if they're the same length, then we never draw an arrow. If they're different lengths, then we draw an arrow pointing from the longer to the shorter. Okay. And in fact, if you think about this for a while, so that the diagram actually uniquely determines the Cartan matrix. So what we have is that Cartan matrix is an equivalent piece of information, an equivalent kind of visual representation of the root system to the Dynkin diagram. Okay. And what's more, it actually, of course, completely determines the root system. So now a root system is called reducible if we can break it up into the union of two non-empty root systems, R1 and R2, such that they are orthogonal. Okay, so this part is crucial here. If this is not possible, if there's no way you can break them up, then they're called irreducible. So maybe it's best to give you a, let's draw, since these are root systems, we have diagrams that we can draw. So let me clear that. So remember the root system, A1. Okay, so it lived inside an R1. And we're going to have, this is the positive, this was the negative of length 1. Now, you see here trivially that we've got the vector and it's negative, and of course, there's going to be no perpendicular vectors in which, so that we can reflect in this root. So it's very easily seen to be, just by looking at it, that it's a root system. But what instead, if we go into R2, and now we look at this, okay, so this is just another copy of the root system A1. And we see that if we reflect in this orthogonal angle here, it just brings this to this and this to this. So it's again a root system. And similarly, if we reflect in this, then it just swaps the two of these. So the root system, this is definitely a root system. But you see that it's actually the union of two non-empty root systems, mainly A1 and A1. And they are orthogonal clearly because everything is at right angles. So this is an example of a reducible root system. Now, the thing is that when you have a reducible root system, anything of interest that you can say about the root system, you can do by looking at the two constituent root systems that you have. You just study them, because basically, because of the orthogonality, the root systems don't really talk to each other. This guarantees that they sort of don't see each other. So there's very little interesting interaction between them. So you could just break it apart into these atoms, these reducible atoms. Somehow, like when we had a semi-simple Lie algebra, we could break it into simple parts and just study the simple parts because they somehow didn't talk to each other. And this is not coincidence that I'm talking about semi-simple Lie algebras with regard to reducibility. So turns out, though, that when you focus and you look at these reducible root systems, that they actually admit a complete classification. So this is an amazing result. It's not at all clear from the definition that they admit a classification. And the proof of the theorem is beyond the first course in Lie theory, so we certainly won't be proving it here. But the result is very easy to state. So amazingly, they break up into 4 families and 5 exceptions. So these are 4 infinite families, 4 infinite countable families, and then 5 exceptions. So the first is A1, our friend, the one that we've been looking at all along. There's a reason we called it A1. It's because the other 4 are then called B, C, and D. So in the homework, I've given you a concrete description, explicit description of the root system B2, and I've asked you to prove that it's a root system. Okay, but of course you don't need anything from this lecture to prove that it's a root system. You just need the material from the previous lecture. Let me stress that. You just need to verify the axioms. You can, of course, for fun, look at this root system and then try to apply what we've learned today, mainly to try to calculate the Weyl group, calculate its Cartan matrix, and so on and so on. But of course, you're not required to do that. And we've got 5 exceptionals: E6, E7, E8, G2, and F4. Why these exceptionals appear is mysterious. Why things classify just into these 4 families, I'm not too sure we really understand yet the meaning behind this, or the meaning why there were 4 families, why there were exceptionals. But these root systems started off in Lie theory, but as people understood them better and better, they were realized to have deep connections to many other areas of mathematics, to differential geometry, to combinatorics, to singularity theory, in physics and string theory, for example. This G2 and F4, sometimes the exceptionals, they appear a lot. Physicists quite like them. They are amazing, mysterious, and deep mathematical objects that people discovered through Lie theory, through root systems associated to semi-simple Lie algebras, as we'll describe in the second part of this lecture. But yeah, it's turned out that there's something deeper than that. Yeah, they're amazing. But we've only so far actually defined the A series. So what I'm going to do is not define the root systems explicitly. I'm going to give you their Dynkin diagrams. That's what I'm going to do. Okay. So what are the Dynkin diagrams? Oh, so I have to clear this. The Dynkin diagrams are as follows. So let's look at the A series. To get a feeling for the Dynkin diagram, you can go to the A series, actually try to show that this is the Dynkin diagram. So let's look at the first one here. The first simple root is just going to be E1 minus E2. Second simple root, remember that the nodes are labeled by the simple roots. The second simple root is going to be E2 minus E3. Now, when you take their inner product, of course, the E1 and the E1 is orthogonal to E2 and E3, so nothing happens there. E3 is orthogonal, sorry, E3 is orthogonal to E1 and E2. So you only get a pairing between, you only get a contribution from the inner product of E2 and E3. Sorry, of E2 and minus E2 and E2, which gives us a -1. And the other way around gives us -1 as well, and the product of this is going to be 1. So, so that gives us one edge between these two here. Now, for the next node, well, of course, we've taken care of this, but the second node, this E2 minus E1, this also has a non-trivial inner product with E2 minus E3, E2, which is E2 minus E3, so it has a non-zero inner product with E3 minus E4. That again gives us 1, so we get one node here, and so on until we come to the last one. And the last one, of course, only pairs with the last simple root, only pairs with this in analogous to the situation with the first node, and that means we just have one here. Okay, so that you can see that's there's not so much mystery about the construction of the Dynkin diagram for the A series. Now, the B series, things become a little more complicated, as you can see from the homework. If, as I said, for fun, you can try to check that this is actually the case. You're not required to, but it might be entertaining. You see, actually, it's the same. It looks almost like the A series, except at the end, we've got this double arrow. So it means that the simple root, and remember, I don't know if I made this, I guess I said this already, but just in case, remember that the choice of base, the choice of simple roots doesn't change the Dynkin diagram. That's not clear, but it's true. The Dynkin diagram is independent of the choice of base. So if you take your, with respect to this ordering, the last root would pair only with this simple root, but the value that you get out of it is actually 2. Moreover, the inner product of this simple root with itself is going to give you 2, and for these it's going to be 4. Okay, so you've got these, actually the length of these roots is longer. And in fact, if you go back to the diagram I gave you for B2, you'll see in comparing the diagrams of B2 and A2, that in A2 all the arrows of the root system were the same length. But for B2, we had vectors which were of different lengths. And that's why the arrow appears inside here. For Cn, this is similar. Again, C only starts after 3. This becomes a 3-dimensional root system, so it's harder to draw and harder to sort of keep in your head. But you'll see inside, if you were to look at a picture of the 3-dimensional, like I said, 3-dimensional picture of the Dynkin diagram for the C3 system, then you would see that they actually have different lengths. That the roots have different lengths, and that is realized here in the fact that we have an arrow pointing. And this time it's a different situation. It's this single root here at the end actually has a norm, has a length greater than the other ones, which all have the same length. See, they all, because if this is the same length as this is the same length as this, then of course by transitivity of equality, they must all have the same length. For Dn, and I should probably say here, there is an important duality between the two of these, because you see the diagrams look very similar. It's just that these arrows are reversed. So these two are somehow dual to each other in some sense. The D series, we get something a bit stranger. See, as we go on, things become successively stranger. Here, at least one thing about it is that the length of the roots are all the same, which is good. But we have this very special root here that has a non-zero pairing with 3 other roots. That doesn't happen up here. Everything is paired either with 1 or with 2 at most. Here, this special root pairs with these 3, this, and this. So it, this is the special behavior in the D series. And then we get to the exceptionals, where things become stranger. So again, we've got a pairing here with 3, with 3, with 3. Everything is the same length, but we've got this pairing between 3. That's how it looks. And then we've got F4, which has got something, looks a little bit like the B2 or the B series, but the double pairing is in the middle. Now you see there's a problem with this. The G2 has been removed because it fell off the bottom. So, but it's easy, I can just write it in. Okay, so then 9, this is the last one. It's G2. And remember, we gave a picture, an explicit picture of the G2 system. It was quite elaborate. It was in dimension 2. The root space was dimension 2, so the rank is 2. So that means we have 2 simple roots. So the Dynkin diagram is going to have 2 nodes. But it turns out that if you look at the inner product of these 2, we actually get that the value is 3. And this is the only root system for which this happens. You see that for all of the other, you have at most 2. In the majority of cases, it's 1. But it's for these series here, it's 2. And then this G2, it's very strange. It's got 3. And moreover, one root is longer than the other. So we have an arrow pointing from the longer to the shorter root. Okay. This one, as I said, actually is arises a lot in string theory for various reasons. And this is it. This is all of the root systems classified. It's amazing. And this picture is very beautiful. And that's where we're going to leave this lecture, this first half of the lecture. What I will show in the second is that, in fact, simple Lie algebras, this is the amazing fact. Well, this we'll be able to show, not completely explicitly, but we can give you the idea of how it works. That a simple Lie algebra corresponds to an irreducible root system. And this is a bijective correspondence. You're basically we're going to look at the adjoint action of the Lie algebra itself. This gives us a root system, and it actually sets up a bijective equivalence between simple Lie algebras, with finite dimensional simple Lie algebras over C, I should say. So C and finite dimensional. Okay. Finite simple complex finite dimensional simple Lie algebras then are in bijective correspondence with irreducible root systems. But we've just seen that irreducible root systems are classified. So that means that simple Lie algebras are also classified. And that means that our simple Lie algebras break up into these four families, A, B, C, and D, and these exceptions, these 5 exceptions, which is a fantastic result. And that's why we introduce root systems. That's the point of looking at root systems in the first place, is because it allows us to classify semi-simple Lie algebras. So if we think back also to Levy decomposition, we were able to take any finite dimensional Lie algebra, let's say C, and we could break it up into a semi-direct product of a nilpotent and a semi-simple. The nilpotent are unclassified, and this is an extremely difficult problem, an important problem, but extremely difficult, and extremely difficult. But the semi-simple part we see for the Lie algebras is now in this given by these diagrams, by these Dynkin diagrams. So I should say, of course, these are for irreducible root systems and simple Lie algebras. Amazingly, but we know that all of the simple, semi-simple Lie algebras are just direct sums of semi-simple, are just direct sums of simple. So once we understand the simples, we understand the semi-simples. And it turns out that actually the semi-simple Lie algebras correspond to general root systems. And it's simple if and only if the root system is reducible, which is great. Okay, so with that amazing result, I'll leave you. The next installment of this like extra bonus lecture will come hopefully in the next day or two. Okay, thank you.